In today's lesson, we are mastering the factor theorem and how to factorize cubic polynomials. By the end of this session, you will be able to find linear factors of higher degree polynomials and express them as a product of their factors. This is a vital skill in additional mathematics because it allows us to solve complex equations and identify the roots of functions which represent where a graph crosses the x-axis. Let's start with the concept of the factor theorem. The factor theorem states that for a polynomial p of x, a linear expression x minus a is a factor of p of x if and only if p of a equals 0. If p of a equals 0, then x equals a is a root or 0 of the polynomial. Graphically, this corresponds to the x-intercepts of the function y equals p of x. For a cubic polynomial, we typically find the first factor by trial and improvement. We test integer values of x that are factors of the constant term d. Let's look at an example. Factorize p of x equals x cubed minus 6x squared plus 11x minus 6. The constant term is negative 6. We test factors like plus or minus 1, 2, or 3. Let's test x equals 1. Substituting 1 into the polynomial, 1 cubed minus 6 times 1 squared plus 11 times 1 minus 6 gives us 0. Since p of 1 is 0, x minus 1 is a factor. Once we have one linear factor, x minus a, the cubic can be expressed as the linear factor times a quadratic factor. We find this quadratic using algebraic long division. Now let's solve a full example. Factorize f of x equals 2x cubed minus 3x squared minus 3x plus 2. Step 1. Find a root. Let's test negative 1. F of negative 1 cubed minus 3 times negative 1 cubed minus 3 times negative 1 squared minus 3 times negative 1 plus 2. This simplifies to negative 2 minus 3 plus 3 plus 2, which equals 0. Step 2. Divide the polynomial by x plus 1 to find the quadratic quotient. Using long division, we find the quotient is 2x squared minus 5x plus 2. Step 3. Factorize the quadratic factor. 2x squared minus 5x plus 2 splits into 2x minus 1 times x minus 2. The fully factorized form of the cubic is x plus 1 times 2x minus 1 times x minus 2. Graphically, the roots are where the curve intersects the x-axis. Here, the roots are x equals negative 1, half, and 2. To summarize the process, first use the factor theorem to find one root. Second, identify the linear factor. Third, use long division to find the quadratic quotient. Finally, factorize that quadratic completely and state the three linear factors. Let's start with the fundamental tool of this topic, the factor theorem. The factor theorem states that for a polynomial p of x, a linear expression x minus a is a factor if and only if p of a equals 0. Why does this work? Essentially, if plugging a value a into the function results in 0, it means there is no remainder when dividing by x minus a. This means x equals a is a root or a 0 of the polynomial. Graphically, this is where the curve of the function intersects the horizontal x-axis. Knowing just one root gives us a gateway to breaking down the entire cubic expression into simpler parts. Let us apply the factor theorem to find the first factor of a cubic polynomial. Suppose we have p of x equals x cubed minus 6x squared plus 11x minus 6. To find the first factor, we use trial and improvement. We test integer values of x that are factors of the constant term, which is negative 6. So we should test plus or minus 1, 2, 3, or 6. Let's try testing x equals 1. Substituting 1 into the polynomial, we get 1 cubed minus 6 times 1 squared plus 11 times 1 minus 6. This simplifies to 1 minus 6 plus 11 minus 6, which equals 0. Because the result is exactly 0, the factor theorem confirms that x minus 1 is a linear factor of this polynomial. Once we have found one linear factor, say x minus a, we can express the cubic polynomial as a product of that factor and a quadratic factor. To find the missing quadratic part, ax squared plus bx plus c, we need to divide the original polynomial by our linear factor. In the exam, you can use algebraic long division or the method of equating coefficients. Long division is often the most reliable way to ensure you don't miss any terms. By reducing a cubic to a quadratic, we turn a difficult problem into one we already know how to solve using the quadratic formula. Or factoring by inspection. Let us factorize the cubic polynomial f of x equals 2x cubed minus 3x squared minus 3x plus 2 completely. First, we use the factor theorem. Let's test x equals -1, as it is a factor of the constant 2. Substituting -1, we get 2 times -1 minus 3 times 1 plus 3 plus 2. Since the result is 0, x plus 1 is our first factor. Note the sign change. If the root is -1, the factor is x minus -1, which is x plus 1. Next, we divide the cubic by x plus 1 to find the quadratic factor. 2x cubed divided by x gives 2x squared. Multiplying back and subtracting leaves us with -5x squared. -5x squared divided by x gives -5x. Subtracting that product leaves 2x. Finally, 2x divided by x is 2. The remainder is 0, confirming x plus 1 is a factor and giving us the quadratic 2x squared minus 5x plus 2. Now, we factorize the quadratic factor further. 2x squared minus 5x plus 2 factors into 2x minus 1 and x minus 2. The fully factorized form of our cubic polynomial is x plus 1 times 2x minus 1 times x minus 2. Visualizing these factors helps us understand the relationship between algebra and geometry. When we have a fully factorized cubic polynomial, we can immediately identify the roots. From our previous example, the factors were x plus 1, 2x minus 1, and x minus 2. Setting each factor to 0 gives us the roots at -1, 0.5, and 2. On a graph, these roots are the x-intercepts, the specific points where the curve cuts through the x-axis. Notice that the constant term in the original polynomial, which was positive 2, corresponds to the y-intercept. This is because when x is 0, all terms involving x disappear, leaving only the constant. Being able to move between the algebraic factors and the graphical intercepts is a high-level skill frequently tested in IGCSE exams. Let's look at a typical Cambridge-style question. Show that x minus 2 is a factor of f of x equals x cubed plus 2x squared minus 5x minus 6, and hence factorize the expression completely. To show it is a factor, we must prove f of 2 equals 0. Substitute 2 into the function. 2 cubed is 8, 2 times 2 squared is also 8, minus 5 times 2 is 10, minus 6. 8 plus 8 is 16, and -10 minus 6 is -16. The sum is 0. Since f of 2 equals 0, x minus 2 is a factor. Now, we use long division or inspection to find the quadratic factor. Looking at the first and last terms, x times x squared gives x cubed, and -2 times 3 gives -6. By checking the middle terms, the quadratic factor is x squared plus 4x plus 3. Finally, we factorize the quadratic. We need two numbers that multiply to 3 and add to 4. Those are 1 and 3. The completely factorized expression is x minus 2 times x plus 1 times x plus 3. In the exam, small errors can cost you many marks. Let's look at how to avoid them. The most frequent mistake is getting the sign wrong when moving from a root to a factor. If the root is positive 2, the factor is x minus 2. Remember, the factor is always in the form x minus a. If a is negative, it becomes x plus a. Many students stop after finding the quadratic factor. If the question asks to factorize completely, you must check if the quadratic can be broken down into two further linear factors. If it cannot be factorized further, state that clearly. When equating coefficients or using long division, ensure you account for the coefficient of the x cubed term. If the polynomial starts with 2x cubed, your quadratic factor will likely start with 2x squared. Always expand your final answer mentally to check it matches the original leading term. Long division involves a lot of subtractions. A common mistake is failing to subtract a negative number correctly, which actually means adding. Double-check your signs at every subtraction step. To secure those top grades, here are some specific tips for your IGCSE exam. When performing trial and improvement, only test factors of the constant term. If the constant is 6, don't waste time testing x equals 4 or 5. Focus on plus or minus 1, 2, 3, and 6. If a question says, show that x minus a is a factor, you must explicitly write down the substitution and the final step where you show it equals 0. Simply performing long division is often not enough for the first mark. Use the factor theorem directly. Keep in mind that if p of a does not equal 0, the result is actually the remainder when p of x is divided by x minus a. This is the remainder theorem, and it's closely related to our work today. If your calculator has a polynomial solver, use it to find the roots first. This tells you exactly which numbers to test with the factor theorem, saving you precious minutes during the exam. However, you must still show the manual substitution to gain full marks. Now it's time for you to practice. I have prepared 3 questions for you. Please pause the video here, solve them on paper, and then resume to check your solutions. Question 1. Show that x minus 1 is a factor of f of x equals x cubed plus 4x squared plus x minus 6. Question 2. Factorize g of x equals x cubed minus 7x plus 6 completely. Question 3. The polynomial p of x equals 2x cubed plus ax squared plus bx minus 2 has a factor x minus 2. When p of x is divided by x minus 1, the remainder is negative 3. Find the values of the constants a and b. Let's go through the solutions. For the easy question, we test x equals 1. F of 1 equals 1 cubed plus 4 times 1 squared plus 1 minus 6. F of 1 equals 1 plus 4 plus 1 minus 6, which equals 0. Since f of 1 equals 0, x minus 1 is indeed a factor. For the medium question, we first find a root. Let's try x equals 1. G of 1 equals 1 cubed minus 7 times 1 plus 6, which equals 0. So x minus 1 is a factor. Dividing x cubed minus 7x plus 6 by x minus 1 gives us the quadratic x squared plus x minus 6. We then factorize the quadratic to find two numbers that multiply to negative 6 and add to 1. Those are 3 and negative 2. The fully factorized form is x minus 1 times x plus 3 times x minus 2. For the hard question, we use the factor and remainder theorems to create two equations. Using the factor theorem, p of 2 equals 0. This simplifies to 16 plus 4a plus 2b minus 2 equals 0, which gives us 4a plus 2b equals negative 14, or more simply, 2a plus b equals negative 7. Next, using the remainder theorem, p of 1 equals negative 3. This simplifies to a plus b equals negative 3. Now solve the simultaneous equations. Subtracting the second equation from the first gives a equals negative 4. Substituting a equals negative 4 into a plus b equals negative 3 gives b equals 1. So our final values are a equals negative 4 and b equals 1. Here are the key takeaways from today's lesson. To summarize our lesson on the factor theorem, the factor theorem states that x minus a is a factor of a polynomial if and only if p of a equals 0. This is your primary tool for breaking down higher-degree expressions. To factorize a cubic completely, find the first linear factor using trial and improvement with factors of the constant term. Then, use algebraic long division to find the remaining quadratic factor. Remember that the factors of a polynomial directly correspond to its roots and x-intercepts on a graph. If x minus a is a factor, the graph must cross the x-axis at x equals a. Always check if your quadratic factor can be simplified further to ensure the expression is factorized completely. Pay close attention to signs when moving between roots and factors to avoid common marks loss.